In this video lecture, we will introduce the notion of random variables, or more generally, extended random variables, which are the ones that are allowed to take value plus or minus infinity. And we'll see that random variables are nothing but Borel functions on probability spaces. This is certainly not how I like to think of a random variable when I'm working with probability, but this is what they are from a technical point of view. We will start with the definition of extended random variable and then discuss some properties. Most of them will be familiar to you about random variables. Starting with definition, the very simple definition of extended random variable. An extended random variable is a function x from a probability space that is to the real line, to the extended real line, which is measurable with respect to the Borel sigma field. So that's an extended Borel function, which was the topic of the previous video lecture. And as usual, when a measure space happens to be a probability space, we also indicate that in the notation. So we use blackboard boldface P instead of Greek letters mu and nu, and we use capital X instead of lowercase f, g, and h for functions. If we know the probability space, the measure space is a probability space, we use capital letters such as x, y, and z for the functions. But since extended Borel functions are more general, any theorem or property that we know to hold already for extended Borel functions are automatically true for extended random variables. We now discuss what is the distribution of an extended random variable. And it turns out the distribution of the random variable is just a probability measure that we have on the real line, which is induced by that random variable. And we already have the terminology and the tools to define that more rigorously. The distribution of a random variable x is the push forward. This was the topic of a previous video lecture. The push forward measure given by this map x. X is a map, technically speaking, that goes from a sample space to the real line. And, well, it can be the extended real line. And it will be the push forward of that measure. So we know that when we have a map and we have a measure, and let's use P for the measure, this induces a new measure here, which we denote Px. That is the distribution of x. So it's a probability measure on the extended real line, which we denote Px. And this, using previous notation from the first video lecture of this chapter, this will be x star p. This is the push forward, and this is a notation which is more related to how you actually compute these probabilities. This will be just saying Px of A equals exactly this, equals Px of A equals P of x minus 1 of A. And now that we have the distribution of a random variable, we can talk about the cumulative distribution function. And that will be, that describes completely what is the distribution of a random variable, and it is just the measure, the probability measure of all the sets, of all the points together up to x from the left, including minus infinity. And it turns out, of course, if we know the distribution of x, this determines the distribution function, or the cumulative distribution function of x. And it turns out that if we know the distribution, the cumulative distribution function of x, then we know what is the distribution of x. And this is obvious and trivial. That's right here. This is trivial, because f of x is just evaluating this function p of x at a certain specific type of set. What is non-trivial is that knowing what fx is, this determines px. And for that we use properties of uniqueness of measures, which was the topic of last week.